I'm going to make an assumption as the neutral axis is equal to 500, okay? 500, and A is going to be equal to 425 because the formulation of A is equal to A multiplied K, sorry, A equal to K1 multiplied C, K is equal to 0.85, okay? So now let's calculate the strains. 0.003 multiplied the first steel, okay, this is the neutral axis, and the first steel, okay, the location of the first steel, and what is the distance between the first steel and the neutral axis? Look at it, it's 35, right? So 35 over 500, and this is going to be equal to 0.00021, and this is smaller than epsilon sy is equal to 0.001825. So I need to calculate the stress for the bottom steel, okay? So for stress for the bottom steel, it's going to be 200,000 multiplied 0.0021. Sorry, I have another zero here. And 0.21, and it's going to be equal to 42 megapascal. So let's do it for the second one, and this is going to be 0.003 multiply the distance. Let's check what is distance. 250, so 250 over 500, and this is going to be equal to 0.0015 smaller than epsilon sy equal to 0.001825. So let's calculate this stress also. 0.0015 multiplied 200,000, the modulus of elasticity, and this is going to be equal to 300 megapascal. So let's do it for the third one. What is the distance of third one? Let's check. 465, right? 465 over 500, and this is going to be equal to 0.00279, and this is greater than epsilon sy. I don't need to write again. So I'm going to use as stress at the 3 is going to be 365 megapascal. So I guess now we understand how we are going to determine it. Okay, so now let's check stresses. They are positive or negative. Look at here. Yeah, they are above the neutral axis. Okay, they are above the neutral axis. So if they are above, they are positive. Okay, these all are compression. So they are all going to be positive. So let's calculate the forces. For the forces, for force S1 is equal to the area of steel. What is the area of steel? 600, right? Multiplied 0.042, and this is going to be equal to 25.2 kilonewton. Let's do it for the second one. And 600 multiplied, sorry, this is not 600, this is 400. Yeah, this is 400. Yes, the area of this mid steel is 400. Multiplied 0.3, the stress, I divided 1000, so it's going to be 120 kilonewton. So let's do it for S3. So the third steel, and it's going to be 600, the same area, multiplied the stress is 0.365. This is equal to 219 kilonewton. Now we got these three forces. Let's calculate F concrete, because look at here. We have F steel, the bottom steel, and top steel, and the mid steel, and also we have F concrete. Okay, so if you remember, also we have the actual force. So, and 0.85 multiplied design strength of concrete multiplied B. What is B? 300, and multiplied A. A was 425. If you remember. I can show you that at the top of the page. So 425. So this is going to be equal to 1192 kilonewton as the F concrete. So now we have F concrete. Let's calculate the actual force, and this is going to be N is equal to total F S I plus F concrete, and this is, let's apply the formulation, 25 plus 219 plus 120 and plus 1192. And this is going to be equal to 1556 kilonewton. Now you can see that we have determined the actual force. So let's calculate the moment. For moment, look at here how it's going to be calculated. And so now let's check for the forces. Okay, this force actually it's not at this direction, it's also at this direction, because I told you that which forces, okay, which steels are above the neutral axis are their compression. Okay, they are compression. So I'm going to take the moment respect to the midpoint again. So it's going to be, for example, this point. Okay, midpoint. This cannot create any moment, and also for F concrete can create a moment because it's going to affect at this point here. Okay, it's going to be 425 over 2. So now such this we won't take just this force. And 215, it is the moment arm of the top steel and the bottom steel, because they have the same distance respect to the midpoint. 219 minus 25, okay, and plus 1192 multiplied 250 minus 425 over 2. And this is going to be equal to 86 kilonewton meter as the moment. So now I'm going to show you that how it's going to be 425 over 2. Okay, so look at here, this is the concrete block. Okay, this is the concrete block, and we have a concrete force here. Now you can see, so the concrete force has to be applied at the midpoint of the concrete block. But look at here, this one is the midpoint of cross section. Okay, but the application point of, so now it's going to be someplace here. So 425 over 2, and it's going to be 212.5, I guess, something like that. Okay, so I have to take the subtract from the 250 to calculate the moment arm. So this one is for that. So now this part also. Okay, so let's make another assumption and determine the actual force and the moment. So now I'm going to assume that the neutral axis is equal to 300. Now you can see I write here, okay, 300, and A is going to be equal to K1 multiplied C equal to 255 as millimeter. These are all millimeter. Okay, so now let's determine strains for strain at the first steel, this one. Look at here, this is neutral axis. So what is the distance of this steel due to respect to the neutral axis? So it's going to be 165, okay, 165. So it's going to be 0.003 multiplied 165 over the C value is 300. And this is going to be equal to 0.0016 and 5. So now you can see this one is smaller than epsilon sy. So I need to calculate the stress inside this steel. And this is going to be equal to 330 megapascal. Okay, so now let's do it for the second one. And for second, look at here, it's 50 over 300, right? 0.003. This is the yield strain of concrete multiplied 50 over 300. And this is going to be equal to 0.0005. Yes, 0.05, smaller than epsilon sy. And again, I have to calculate the stress inside the steel. and this is going to be 200,000 multiplied 0.005, and this is going to be equal to 100 megapascal. But look at here. Here is compression, here is tension, okay? And this steel at the tension side, so the first steel is negative and the second steel also positive, okay? So let's do it for the third steel, okay? For third steel, 0.003, distance is 265 over 300, and this is going to be equal to 0.00265. And this is greater than epsilon sy is equal to 0.001825. So the stress is going to be used as 365 for the third steel. Okay, so now I got it. So let's calculate the forces. For Fs1, it's going to be the area of the steel multiplied the stress minus 0.33, okay? So this is going to be equal to minus 198 kilonewton. And for Fs2, it's going to be the area of the steel, 400 multiplied the stress, 0.1, and this is going to be equal to 40 kilonewton. Okay, so let's do it for the third one, Fs3, and this is going to be 600, the area of the steel, and we have the 0.365 as the stress, and this is 219 kilonewton. So now I got the forces, but look at here, we have also the concrete force, right? I got 3 forces, but I have also concrete force. Let's calculate the concrete force also. For F concrete is equal to 0.85 multiplied design strength of concrete multiplied B multiplied A. So 0.85 multiplied 0.011 multiplied B. What is B? B is 300 multiplied also A. So let's check for A. A is 255. Okay, A is 255, and the value of F concrete is going to be 715 kilonewton. Okay, so now let's also calculate the actual force, because you know I have an actual force here. Okay, so let's do it. For the actual force, the formulation is this one: total F steel I plus F concrete, and this is going to be equal to minus 198 plus 40 and plus 219 and plus 715, and this is going to be equal to 776 kilonewton. Okay, now we got the actual force. Let's calculate the moment. For the moment, it's going to be calculated respect to the midpoint of the section. Okay, the midpoint of the section. So this is going to turn at this side and turn at this side, and this one at this side, and this all at the counterclockwise direction. So it's going to be calculated like that. 215. It is the same distance for the top and the bottom steel. Okay, so 198 plus 219 and plus 715. Okay, so multiplied 250 minus 255 over 2, and this is going to be equal to 177 kilonewton meter as the moment. Okay, so now let's make a check. Look at here, 715, 250 is the half of the cross section, and this concrete block, and this is the concrete force. So it's going to affect at the midpoint of that 255. So 250 minus 255 over 2. Okay, the moment arm for the F concrete. Now I guess you understand how we are going to do also for this one. Let's do it for the last part, and we are going to draw the interaction diagram. So now I am going to assume the last assumption of the neutral axis is equal to 160 millimeter, and due to this neutral axis, A is equal to K1 multiplied C, 0.85 multiplied 160 is equal to 36 millimeter. Okay, so let's calculate the strain for the first. For the first steel, it's going to be something like that: 0.003 multiplied 305. Look at here. If you can see that this is the neutral axis, okay. And if this is neutral axis, and I'm going to take the distance from the steel to the neutral axis, okay, 205. And this is going to be equal to 0.0057, and this is greater than epsilon sy. So this is going to be sigma for the first one. It's going to be equal to 365 megapascal. But look at here, this is the tension area, this is the compression area, because I told you that above the neutral axis is compression and below the neutral axis is tension. So this is going to be negative, and this is going to be negative, okay? This is negative. So now let's do it for the second one. 0.003, the strain of the concrete, multiplied 90 over 160, and this is equal to 0.001687, smaller than epsilon sy. So this is going to be calculated as S2, 200,000 multiplied 0.01687, and this is going to be equal to 338 megapascal. So now we also got it. So let's do it for the third one. Epsilon S3 is equal to 0.003 multiplied, let's check the distance, 125. Now you can see, okay, 125 over 160 and equal to 0.00234, and is greater than epsilon sy. So the stress is going to be for this steel 365 megapascal. And sorry, I forgot, this is also negative. So now I got the stresses. Let's calculate the forces. For the FS1, look at here, forces. I'm going to calculate this both, all forces. So for FS1, it's going to be the area of steel multiplied the stress inside the steel. What was that? 365. So but minus, okay? And this is going to be equal to minus 219 kilonewton. So let's do it for the second one. 400 the area of the steel multiplied the stress inside the steel minus 0.338, and this is equal to minus 135 kilonewton. So now let's do it for the third one. 600, multiplied the stress inside the steel 0.365, and this is also 29 kilonewton. So now we got the forces. Let's calculate the concrete force. Okay, concrete block force 0.85 multiplied 0.011 and multiplied 300 and multiplied A. What is A? 136. You know, I calculated before. So, and this is going to be, one second, it's going to be equal to 382 kilonewton. So now we got all forces. Let's calculate the actual force. If you remember the formulation of actual force, it's going to be plus F concrete, okay? So it's going to be calculated like that, minus 219 plus 219 and minus 135 plus 382, and this is going to be equal to 247 kilonewton. So now we got the actual force. Let's take the moment for the moment, it's going to be something like that. I'm going to take separately. I'm going to show you. Look at here. These are all there. They will rotate the block at the same direction. For example, this is midpoint. Okay. So now let's calculate the moment. The moment is going to be calculated as 215. The moment arm for FS1 and FS3. Okay, the moment arm for this both forces multiplied 219 plus 219 because they are going to make the same effect, and plus 282 multiplied 250, the half of sorry, and if you remember that I'm going to take the respect to the midpoint of the section, minus a over 2. What is a? A, if you remember, 136 over 2, and the result of this multiplication is going to be 164 kilonewton meter as the moment. Now you can see we got all the moments and the shear forces. Now the question is nearly solved. So now we are just going to draw the interaction diagram, and I have moments on my hand. So let's write the moments here. So now let's draw the interaction diagram. I have the moments on my hand. For the interaction diagram, for example, when the moment was 0, that was 1986. Okay, when the moment was 0, this is a moment, and this is actual force. So, and this is going to be, for example, 30, and I'm going to have a moment here as, for example, it's going to be that point. Okay, and this is going to be 1842. Okay, so now let's write the other moments. So this is going to be, for example, 86. It's going to be 15, and this is maybe this point, 1556, and it's going to be matched at this point, and 177. Sorry, I have a 164 before that. Sorry, I have a 164. For example, this is 164, and due to this one, and this is going to be, for example, this point, okay? Because the moment is respect to that point is 247. So, and for 177, I have 776. 776, for example, half of this one. 776 as the force. So when I match these all points, yeah, for example, I have to take this point to here, but the shape is going to be something like this. I couldn't draw so well, but if you draw at the millimetric paper, okay, you are going to obtain a diagram like this. For example, it's going to be like that. You are going to get something like this. This is going to be the balance point. So now, which point is balanced here? Actually, this one, okay? This point is balanced. So now I guess you understand how we are going to solve the question and draw the interaction diagram. So now the question is solved. Thank you for watching. See you for the next class.